We have Elena Kim speaking about the support of semi-classical measures and hyperbolic manifolds.
Great. Thank you so much for the invitation to speak, and thank you everyone for coming and listening to my talk today. Today I'm going to talk about some brand new work that I put on the archive last week, joint with Nick Miller. So first I'll introduce my setting. So we care about a manifold M, and it's compact, hyperbolic, and n-dimensional. This result is in the field of quantum chaos, so we want some sort of chaos. And so that's why we're working on a hyperbolic manifold. In the setting of a hyperbolic manifold, our geodesic flow is a nocive, which intuitively means it induces some sort of stable, unstable decomposition on the tangent space, which will give us the chaos that we want. I care about these things called semi-classical measures, which I'll define now. So first, I need to take some sequence of eigenfunctions of Laplacian uj. I will normalize them. And this h, which we're using to write the eigenfunction or the eigenvalue, we are assuming it goes to 0. So this h is what I'm calling a semi-classical parameter. In this talk, I will keep talking about taking semi-classical limits, and that just means we're taking the limit as hj goes to 0. Okay, and then we say that uj converge semi-classically to some probability measure mu, which is a measure on the cotangent bundle if the following limit holds. So this is op h of A. If you're unfamiliar with this notation, I'll give some intuition in a second. So we're looking at this inner product. This is the L2 inner product of our manifold. And we want to converge this to converge to the integral over the cotangent bundle of our function A with respect to our measure d mu, or with our respect to our measure mu. If this limit holds, then we call mu a semi-classical measure. So just intuitively speaking, you can think of semi-classical measures as characterizing the mass of the eigenfunctions of the Laplacian in the semi-classical limit.
I won't say we, I'll just say me, or some of us, meaning possibly just me, might not know what some of that means. So what is this op n?
Perfect. Yeah, let me give you some intuition right now.
Okay.
Also, should it be hj to the -2?
Yes, you're right. Thank you. Yep, so the eigenvalues are going up to infinity, the semi-classical limit's going to 0. Okay, so if you're familiar with microlocal analysis, op h is the standard quantization. If you're unfamiliar, let me just give some intuition in a really simple case. So my simple case is when my manifold is Euclidean space. This obviously is not a compact hyperbolic manifold, but the quantization, it doesn't depend on the hyperbolic structure. So this is our simple case. Then I'm going to write my function x, you can think of these are the first Rn variables, and c, you can think of the tangent space. So if this splits neatly into a function on x and a polynomial in c, then when we quantize our function, it'll just be multiplication by b, and then it'll turn into a derivative corresponding to the c coordinates. So always our intuition for this is we want in x, it's going to act like a multiplication operator, and c, it's going to act like a Fourier multiplier. Obviously, it can get more confusing if it's not in this simple form, but this is the simple example to keep in mind. So you can just think of this, if you're unfamiliar, as a generalization of a differential operator. Oh, I forgot to mention up here, this is, we want this to hold for any smooth function of the cotangent bundle. Okay,
So just intuitively, you're acting by, so the function on the tangent space is acting by derivatives. Is that what you're saying?
yes,
Yeah, okay, and
yes. So derivatives, it's a Fourier multiplier.
But will you write there H V over like what are these letters?
This is the derivative.
Yeah.
This H is my semi-classical parameter.
what's in the denominator?
Oh, this is an I, the imaginary I.
Unimaginary.
Classical parameter.
So my semi-classical parameter is my H. And so this is in the field of semi-classical analysis, so we always care what happens when we take some limit as H goes to 0. If you were a physicist, you would say H is Planck's constant. But in my world, we care about H going to 0.
Something like 1 over the
Okay, so we have our semi-classical measure. Now I want to define some facts about the semi-classical measure that we'll just take for granted. So the first one is semi-classical measures are invariant under the geodesic flow, which I'll denote by phi t. And then the second one is if mu is a semi-classical measure, the support of the semi-classical measure is contained in the cosphere bundle. Okay. So the first major result about semi-classical measures is called quantum ergodicity theorem. And this is due to Schnurleman, Zeldich, and Cohen de Verdier in the 70s and the 80s. And so what their theorem basically says that if we have a negatively curved compact manifold, which is a slight generalization of my hyperbolic setting, there exists a density one sequence of eigenfunctions of the Laplacian that converge semi-classically to the Liouville measure. So intuitively, what this result says is that you can expect a sequence of eigenfunctions to the Laplacian to equidistribute in the semi-classical limit. Then the other major thing that I want to talk about is known as the quantum unique ergodicity conjecture. And this is due to Rudnick and Sarnak in 1994. And they conjectured that actually the Liouville measure is the only semi-classical measure. So intuitively speaking, any sequence of eigenfunctions would equidistribute in the semi-classical limit. This conjecture remains open. However, there's one regime where some partial progress has been made, which is known as the arithmetic case. This is not where my work falls in, but it has been, anyways, I think it's an important thing to talk about, so I will mention that. So in the arithmetic case, we're gonna make a couple restrictions.
It was in this room that the connection was discovered.
Oh, really?
Yeah.
I'm glad that I'm mentioning it in this room then. Right, so the first restriction we're gonna make is we restrict to arithmetic manifolds. And the nice thing about restricting to arithmetic manifolds is we have the existence of Heck operators, which are averaging operators, and they are a commuting family of bounded normal operators, and they also commute with the Laplacian. And then to look at the arithmetic case, we want to restrict to joint eigenfunctions of the Laplacian and Heck operators. So under these restrictions, quantum unique ergodicity is known as arithmetic quantum unique ergodicity, which I'll abbreviate by AQUE. So the first result in this is due to Lyndon Strauss in 2006, and he proved arithmetic quantum unique ergodicity for compact hyperbolic surfaces. The next result I want to talk about is due to Sundar Arajan in 2010, and he proved arithmetic quantum unique ergodicity for the following modular surface. So this is not a compact surface. Then more recently, we have some results in higher dimensions. So due to Shatantov and Silverman, in 2022, we now have arithmetic quantum unique ergodicity for compact 3 and they're hyperbolic, of course. And now the state of art in higher dimensions is also due to Shatantov and Silverman in 2024. And in this setting, and this is in 4 dimensions, so we have partial results towards arithmetic quantum unique ergodicity in 4 dimensions. And currently nothing is known in higher dimensions. Okay, so with this one. Okay, so that is one area of work motivated by the quantum unique ergodicity conjecture. My area falls into a different category, which very loosely I'll call work that uses the fractal uncertainty principle to get information about the support of semiclassical measures. So a little brief history about this. This is not inclusive of all the results due to time constraints for today. So the first result I want to mention is due to Dyatlov and Jin in 2018, And they were able to prove that all semiclassical measures on compact hyperbolic surfaces have full support. So just to clarify what I mean by full support, as I mentioned before, the support of semiclassical measures is contained in the cosphere bundle. So this means the support is equal to the cosphere bundle. Then more recently, due to Atherea, Dyatlov, and Miller being the Nick Miller that I collaborated on my project with in 2024, they looked at compact, specifically complex, hyperbolic manifold. So this is a higher dimensional case. And they showed that if you have a semiclassical measure, mu, the support of your semiclassical measure needs to contain the cosphere bundle of some manifold sigma, where sigma is a compact, immersed, totally geodesic, complex submanifold. Okay, so now I will present my result and then I will compare and contrast with these previous results. Okay, so first, just a little bit of notation. I will denote the coframe bundle by F star M, and you can write an element of the coframe bundle in the following form. Where X is a point on my manifold, and C1 through Cn are points, the cotangent space at X, and they form a positively oriented orthonormal basis. Then I need to fix the following immersion, and this is going to send pi s is going to send points from the coframe bundle to the cosphere bundle, and it's given by the following explicit. Okay, finally, this part I'm going to be a little vague about, but I'm going to let U1 minus be a vector field on the coframe bundle, and it will generate the cyclic flow. Okay, now that we've gone through that notation, here's the result. So M is a compact hyperbolic N manifold, and I will assume that mu is a semiclassical measure. Then there exists some point on the coframe bundle such that the following set is contained in the support of the semiclassical measure. So again, T.
This is a zoom from far away. What do you mean by cyclic flow? This is a one parameter flow? This is a multi-parameter flow? What are we talking here about?
Oh, that's a good question. This is specifically a one parameter flow.
So it's not cyclic. Cyclic for me basically means the full unipotent. One parameter, very good.
Okay, yeah, so this is a one parameter unipotent flow.
Very good.
Okay, so We're looking at this set here. And this is contained in the support of my semi-classical measure. So recall again, this is my geodesic flow. This is my 1 parameter unipotent flow. And this is contained in the support of the semi-classical measure. So this is the result that you get by using the fractal uncertainty principle, which I'll explain later. But through the work of my collaborator, Nick Miller, he was able to use Rautner theory to further characterize this set. So his result says for a point Q on the coframe bundle, any point this set, the same set as above. This is equal to the cosphere bundle of some submanifold sigma Q. And here, right at the bottom, can you guys see in the back? Okay, so sigma Q is the minimal compact immersed totally geodesic submanifold such that X coming from here is on the manifold, and C1, C2 are part of the cotangent space of the manifold up at X.
Wait, so you said that the first of these theorems is yours with Nick Miller and the second one's just Nick Miller, or?
I guess this is more my result and this is more Nick's result.
Okay.
I mean, the second one is sort of essentially, right, follows from Shah's theorem, as far as I can see.
Premise what?
It's a version of it's a version of Nim's result. Yeah.
I mean, it's basically, it's a theorem of Shah, I'm sorry. The second result.
So a little bit to compare and contrast this result with the previous results. So all these results use the fractal uncertainty principle to analyze the stable and unstable subspaces of the cotangent space. And the difference between my result and the previous results is when these previous results use the one-dimensional fractal uncertainty principle, which was the only tool available at the time. And I was able to exploit the recent generalization by Alex Cohen of the fractal uncertainty principle to higher dimensions. So in this case, where we're just looking at surfaces, the unstable space and the stable space are both one-dimensional, so you can analyze them using the one-dimensional fractal uncertainty principle. That is not true on higher dimensional hyperbolic manifolds. However, on specifically complex hyperbolic manifolds, there's a single one-dimensional direction where the geodesic flow expands the fastest, and a single one-dimensional direction where the geodesic flow contracts the fastest, and you're able to use the fractal uncertainty principle to look at those one-dimensional spaces. That's not true in the real case, so that's why this result was only able to be proved after the extension of the fractal uncertainty principles to higher dimensions.
So is there a way, just because there's a lot of stuff that I'm less familiar with, but I kind of know the picture of the flows. So so your theorem, I guess, which is the first one, is there either a picture you can draw or a way of just, you know, and it might be there in the symbolism, I just that to like phrase it in terms of the stable directions or something?
No. I mean, this is was a surprise when it was proved. No, this is a theorem. It's not something you could explain with 3 words or something.
Or is there a way to? Yeah, I'm having trouble visualizing it. Is there a visual
it's important that it's not the full unstable that you're
Okay.
taking. So you have this point Q,
Okay,
you take a one parameter piece, okay? But
Okay.
it's not the full unstable, it's just one direction in the unstable.
okay,
So the quantifiers, there exists a point, so
okay,
yeah. One direction in the unstable, and then well, basically what happens is that you expand it, okay?
okay.
And throughout this whole, the whole expansion is contained in the support of the measure. And if you want to visualize it, you should look at the second theorem.
I don't know how to visualize the second there, but what you said was really helpful. Thank you.
Yeah, so another thing I wanted to mention about this is why there's full support in the two-dimensional cases, but in higher dimensional cases, we're left with these compact immersed, totally geodesic submanifolds. And that is just due to the fact that this one perimeter unipotent flow is not uniquely ergodic in dimensions 3 or greater. In dimension 2 it is, and they're able to exploit that to get full support, but we do not have that in higher dimensions. One last comment I wanted to make is this work is all inspired by quantum unique ergodicity. And if that quantum unique ergodicity were to hold, then all semi-classical measures would have full support. So the question is there any cases here where this does give full support? So we know there are many examples of three-dimensional non-arithmetic hyperbolic manifolds with no totally geodesic submanifolds. So there we get full support. Another trivial observation is because of this fact here, sigma q is at least two-dimensional. So then that replicates this result of full support in 2 dimensions. We don't know anything if for higher dimension, non-arithmetic hyperbolic manifolds, if there's any cases where we can rule out totally geodesic submanifolds. So that's all we can say for that. Okay, so for the remainder of my talk today, I want to try my best to explain some of the key ideas of what is the fractal uncertainty principle and how can it give us this result. But in order to do this, I'm not going to prove this theorem for you. I'm instead going to talk about some previous work I did on a toy model known as quantum cat maps. This is a discrete toy model, so hopefully it's easier to understand, and I can also draw nice pictures for everybody. So that is what I want to do. Okay. So first, a little notation on this one. So a new object that I care about is I'm looking at the symplectic 2n by 2n integer value matrices. Just to review, a matrix A is symplectic if and only if it preserves the standard symplectic form, i.e. we have this for any z and omega. Okay, so now let me explain how my toy model works. I'm going to make some replacements. So before I had a hyperbolic manifold, and now I have a 2n dimensional torus. More accurately, I'm replacing the cotangent bundle of our manifold. So this is even dimensional, that's even dimensional. We're happy.
What exactly is your standard symplectic form?
Oh, yes, I'll give you a definition. So if I write here, x, c, that does something looks wrong. X, this should be,
So 0 identity minus identity 0.
okay, and then before I had the geodesic flow, and I'm going to replace this by a symplectic matrix A. So for the rest of the talk, anytime I have a capital A symplectic matrix, I wanted my symplectic matrices to be integer valued because then it will be an automorphism of the torus. Finally, I had the Laplacian before, and I am replacing this by something I'm calling a quantum cat map, which is something I will define later. But really you can think of this, it's a quantization of the symplectic matrix A. So before we had some stable, unstable behavior on the geodesic flow. Now I'll just assume my symplectic matrix has some non-unit length eigenvalues, then that will give some stable, unstable behavior. Okay, finally, before I had my semi-classical parameter H, and that was given by the eigenvalues. This time, it's given by the following, so it's inverse 2 pi n, where n is some even integer. This is kind of technical and it has to do with the quantization of our symplectic matrices, but we'll just accept this for today.
Can you say an absolute more about the quantization?
Of the quantum, yeah, if you wait a second, I'll give some more intuition, yeah. So before, when I was taking my semi-classical limit, I was always taking h to 0. Now, obviously, this is equivalent of taking a sequence of n off to infinity. Okay. So. Okay, so to define a quantum cat map, first I'm gonna have to explain how I'm gonna quantize my functions on the torus. So my goal is if I have some function on the torus, I want to send it to an operator, which I'll denote by op n of A, and it will map complex vectors to complex vectors, Cn to Cn. So as I mentioned before, the idea always is that we want in the x variable things to act like a multiplication operator, and in the c variable things to act like a Fourier multiplier. So in this case, I will have this is a discrete model. I'm going to have a discrete Fourier transform. So this is Fn sends complex vectors to complex vectors, and it's given by the following explicit form. So I'm looking at the jth coordinate. So it's a normalization constant in the front, and then the following sum. Okay, so this is my discrete Fourier transform. Then if
So what did you write there in the exponent? Just purely
This-
in the exponent of the e to the 2.
negative 2 pi ijk
Okay.
over n. Great. So this intuition, it's an important caveat that I should have mentioned earlier. This is all going to be in the simplest case where the dimension of my torus is just 2. Okay, so this is our discrete Fourier transform. So now some simple cases. The first simple case is what if my function is only a function of x? Then as we want it to be, it'll act like a multiplication operator. So here it's acting on my vector f, looking at the jth coordinate, its action. And this is what we'll get. And then the other end of the spectrum for simple cases is what happens when it's just a function of c. Then as we want it to, it'll act like a Fourier multiplier. So again, this is what happens at the jth coordinate. Okay, so this is all I'll say for now for the quantizations of functions on the torus, these discrete quantizations. Now I want to get the definition of a quantum cat map. So a quantum cat map corresponding to my symplectic matrix A is a sequence of unitary operators. Mn, and they'll send Cn to Cn such that for any smooth function on the torus, the following holds.
Oh, by the way, that kind of got cut off. So for all eigen C infinity,
On the
Maybe.
torus.
yeah, should be like on the next line or something, because the board kind of gets cut off for.
Okay, that's good to know. I'll stop writing that close to the edge for the next line.
Perfect.
Okay, great. So if we take op n of A and we want to conjugate it by our quantum cat map, it's the same as taking op n of our function A composed with our symplectic matrix A. So quantum cat maps are all the unitary operators that satisfy this relation, and this is known as an exact Egorov theorem. Exact because there's no remainders term, it's an actual equality. And it turns out, I'll just state this as a fact, for each fixed n, the family of quantum cat maps corresponding to that n is unique up to a phase constant. Okay, so now I'll explain results for quantum cat maps, and then we'll see that it is similar to the results for hyperbolic manifolds.
How is this similar to the classical cat map and why is it called cat map?
That's a great question. So you can think of these symplectic matrices as a generalization of Arnold's cat map. And then we're quantizing them, so quantum cat maps. Okay, so for some assumptions, we will suppose A, our symplectic matrix, has at least one non-unit length eigenvalue. This is going to give us some chaos. It's a simple fact about symplectic matrices that if lambda is an eigenvalue, lambda inverse is also an eigenvalue. So this will give us both stable and unstable behavior. Okay. I also want to assume that A is diagonalizable over the complex numbers. You can actually say something slightly weaker than this, but for the sake of simplicity, that's what we'll go with. And then finally, I'm gonna let E plus and then E minus be the real part of the eigenspaces corresponding to the largest corresponding to E plus or smallest E minus eigenvalues. So you can think of E plus as the space, the real space that grows under A, and E minus is the space that contracts under A. Then here's the theorem. Mu will be a semiclassical measure associated to A. Then there exists some point on the torus and some vector in either E plus or E minus non-zero, such that the following set is contained in the support of my semiclassical measure. I never explicitly defined what I mean by semiclassical measures for quantum cat maps, but it's pretty analogous to hyperbolic surfaces or hyperbolic manifolds, but the eigenfunctions are instead eigenfunctions of the quantum cat map. So this set is contained in the support of the semiclassical measure.
This is your theorem of that, like, broadly generalized or something?
Yes, this is my theorem from a previous paper.
You mean R plus, RV, right?
Oh, RV, yes, thank you so much. Okay. I guess first I'll just do a little discussion of this theorem and then we'll compare and contrast. So the paper where this result appeared also contained an appendix by two number theorists, Teresa Anderson and Robert Lemke Oliver, who are able to use this result plus some number theory to show that generically semiclassical measures have full support on the torus. However, famously, quantum cat maps is an example where quantum unique ergodicity, or I guess the analog of quantum unique ergodicity, does not hold. The first example was due to four Nonomacher and Debiev, and they found an example in 2 dimensions that has full support, but it is not the uniform measure. And I was able to generalize their example to 4 dimensions to find an explicit semiclassical measure whose support matches this setup here, but the support does not have, but the semiclassical measure does not have full support. So now to compare these 2 results here. So in this above result here, the X is replacing our Q. And then, as I mentioned, our symplectic matrix A replaces our geodesic flow. And then finally, this 1 parameter unipotent flow is being replaced by V up in that case there. So even though everything's replaced, they are actually pretty analogous theorems. Okay. I guess I have 18 minutes left. I'll try my best to prove this.
You have 22.
I have 20, okay, I'll take it. So this proof idea that I'm going to talk about today, it generalizes previous results by Dyatlov and Jin on quantum cat maps, and also the work that I mentioned of Dyatlov and Jin on hyperbolic surfaces. The main novelty to this is that it is an application of the higher dimensional fractal uncertainty principle. Okay, so here is the proof. It's more of a proof outline. So I'm going to take some sequence nj going to infinity. As I mentioned before, this is equivalent to taking the semiclassical limit, and I am going to let uj be a sequence of normalized eigenvectors of my quantum cat maps M and J. And I will suppose that these eigenvectors are converging semiclassically to my semiclassical measure mu. Okay, so then I want to suppose towards a contradiction that for all points X on the torus and for all vectors B in E plus or E minus that are non-zero, the set X plus RV mod Z2N intersects the complement of the support of the semiclassical measure. So I make this assumption towards a contradiction. Once a contradiction is proven, then clearly we have, there exists some X and some V that this set here is contained in the support of the semiclassical measures. Analogously to how on hyperbolic manifolds, semiclassical measures were invariant under the geodesic flow, they're invariant under the symplectic matrix. So then I can apply all these powers, and then that shows the theorem. So all we need to do is find some sort of contradiction. So the first thing I'm going to do is construct a partition of unity, on my torus. So it's gonna have two parts, B1 and B2, and they need to have two properties. So the first one is for all x points on the torus and v in either e plus or e minus. X plus RV mod C2n intersects the complements of the support of B1 and the complements of the support of B2. The second property is that B1 is supported away from the semi-classical measure. So the construction of this partition of unity is non-trivial, but today we'll just take it as a fact. Then I want to set Bi, I being either 1 or 2, to be the quantization of these functions Bi. This gives what is called a microlocal partition of unity, i.e. we're gonna have these two operators sum to the identity. The main idea of this proof is to use this partition of unity B1 and B2 to construct something that we can handle with the fractal uncertainty principle, which first I will actually need to explain. So the fractal uncertainty principle uses two important definitions called line porosity and ball porosity, which I will demonstrate with pictures. So here I'm going to construct some sort of line porous set X. And so to construct a porous set, I'm gonna take this box and I'm gonna put a bunch of holes in it. So all of these holes are things that are no longer contained in my set X. So I wanna have a couple big holes and a lot of small holes to fill in the gaps. And so line porosity says that if we take some line on our set, or we take some line in Rn, the line can't be too big, it can't be too small. We can find some point. We can find some point on the line such that if we make a ball centered around that point, the size of the ball is proportional to the size of the line. That is gonna be not contained in X. The concept of ball porosity is similar. But instead, I want to take a ball that's not too big and not too small. And I need to find, there always exists some point inside my ball such that if I draw another ball that's centered at that point, it's not going to be contained within my set.
Proportional to the.
Yes, and the size of this ball is proportional to the size of the original ball. Line porosity is a stronger property than ball porosity. It implies ball porosity. A very simple example of a ball porous set on, this is my R2 plane, would just be a line. Okay, so those very loosely are the definitions. So now I can explain what the fractal uncertainty principle actually says. So this is the higher dimensional version of the fractal uncertainty principle due to Alex Cohen in 2023. And his theorem says that if we have some set X contained in this n-dimensional rectangle, and it is porous on balls from scales h to 1. So by scales h to 1 is what I mentioned before. We want our balls to not be too big, not be too small. The diameter of the balls needs to be bounded between h and 1. I'll also mention that I am simplifying his theorem a little bit for the sake of exposition today. And so we want another n-dimensional set to be porous on lines from scales h to 1, then the following holds. There exists some beta and c greater than 0, such that we take the indicator function of x, the semi-classical Fourier transform, which if you're unfamiliar with this, is just the standard Fourier transform, but it's been rescaled by our semi-classical parameter. Indicator function of y, and we're looking at the L2 to L2 norm of this. It is bounded by ch to the beta. So in the semi-classical limit, this will decay to 0. Okay. So the idea is that somehow I can use my partition of unity B1, B2 to create something that's porous. So let me draw some pictures illustrating this idea. So here is my torus, and I will draw a cartoon of maybe, let's say, the support of B1. Okay. So this shaded in region is the support of B1. Because of my property 1, for the partition of unity, this cartoon picture is vaguely accurate. It will at least accurately provide us intuition. So this is the support of B1. Now I want to take B1 and compose it with my symplectic matrix. As I mentioned, it has some eigenvalues greater than 1 and less than 1. So we're going to get some stretching in one direction and some squeezing into the other. Now if I take the support of B1 composed with a large power of our symplectic matrix, then it will eventually stretch so much it will start wrapping around and look like something like this. So here's the last picture I want to draw. So what happens then if we take the product of the support of B1 composed with many different powers of the symplectic matrix? So here K will range from 0 to some integer t. Then we'll have the original hole, and then the stretched hole, and then it will really stretch around. So the main intuition that we are meant to get from this picture is that if we look at this unstable direction here, things are relatively uniform. If we start in a hole, we're going to continue to be in the hole generally. If we start outside of the hole, we'll stay outside of a hole. But in this stable direction, things look relatively porous. So that's our intuition. Because I can only draw a 2-dimensional photo on the board, here we only have a 1-dimensional porous set, but you can imagine in higher dimensions, we get a higher dimensional porous set. Okay, so that's our intuition. To get porosity, we need to take B1 or B2, compose it with powers of the symplectic matrix, and then take a bunch of the product and take the product of that.
Can I ask a very silly question?
Mm-hmm.
Why is it called the fractal uncertainty?
So these porous sets are going to have some fractal qualities. A very simple example of a porous set would be the standard 1/3 Cantor set.
Okay.
So it's kind of saying that if our set is fractal in some sort of way, we get an uncertainty type principle.
So in your set, in your settings, for B1 is what you're thinking of as a, or so your porous set is the one transversal for the direction of the stretch.
Yeah, so my porous set is kind of the projection
Right.
onto in the stable direction. Very loosely speaking. Okay, so then putting this intuition in practice, if we, from our exact Egorov theorem that we use to define quantum cat maps, we know that if we take op n of B1 or B2 and we compose it instead with a power of the quantum cat map, it's the same as taking B1 or B2 and compose it with the power of the symplectic matrix. So this allows us to have this statement that we want on these functions and put it onto the operators. So I will define this as Bij. So it's this propagated version of our operator. And then what we want to do is we want to take products of these operators here. So to do that, I'm looking at the set of words of length 2t. These are words with letters 1 or 2 of length 2t. And if W is a word of length 2t, we can write it as the following. So each of these letters is either going to be a 1 or a 2. So then we can use this concept of words to have an easy way to compose these operators with each other. So I'll define BW to be composition of operators given by the words. And the important thing about this is using a little microlocal analysis up to a decaying error term that I'm going to ignore. This is equal to the quantization times n. So this up to an error term that I'm ignoring is equal to the quantization of this product here, which is the B1s and the B2s propagated by A in the negative direction and then propagated positively. And that is really helpful because this exactly aligns with this up here, which is the thing that's going to give us porosity. Okay, to simplify notation a little bit, I'm going to set this product here to be equal to B plus and this product here equal to B minus. Then if I set omega plus or respectively omega minus to be the projection of B plus or respectively B minus onto E plus or E minus. Remember that this E plus was the fast growing space, E minus was the fast shrinking space. Based on the intuition that we got from these pictures, omega plus and omega minus should both be line porous sets. So now we've constructed explicitly something that is porous. Okay. Now just to quickly finish up the proof, maybe I'll finish over here.
Only one of them is line porous, no? They are
On hyperbolic manifolds, one will be line porous and one will be ball porous. But
here.
in cat maps, you get the stronger statement that they're both line porous.
Oh,
Okay, so the last thing that we need to do is we are gonna sum up all of our BW operators. So very loosely, I'm gonna let BY equal to the sum of our operators BW, where W is a word with many ones, and BX is gonna be the sum of BW, where W has few ones. Here, the complement of many is few, which gives us the fact that we have another microlocal partition of unity. The nice thing about this is that it tells us we can use the triangle inequality to get this here. So our contradiction would then be proven by showing that this part decays to 0 and this part decays to 0. So here By is the sum of these operators where they contain many ones. And this is where we go back to our partition of unity and we look at property number 2, which says that the B1 is defined to be supported away from the semiclassical measure. That tells us that this first operator by applied to our eigenfunctions is going to decay to 0. The second part we will deal with the triangle inequality. So here we can bound it by the number of terms in the sum making this operator, and then the maximum of its summands. So this here, the number of terms in the sum, we really don't need to worry about it. We can just kind of fine tune what we mean by many and by few. So that's really not something to worry about. The crux of the argument is arguing that this BW decays to 0. Luckily, using the work on the board over there, looking at this here, this is equal up to a decaying error term that I'm ignoring. This is equal to op n of B plus times op n of B minus. And it turns out that the decay of this here is equivalent to showing that the following decays. The indicator function of omega plus, semiclassical Fourier transform, indicator function of omega minus. And now we're actually done, because we claimed over on the last board, maybe I didn't write it down, but this omega plus and omega minus are both line porous. And so we have something that exactly aligns with the fractal uncertainty principle. So then we know that there exists some H or some C and some beta such that we have the following bound, which decays to 0. So we get this here, all decays to 0, and that completes the proof.
Any questions? So it's in this picture, what are the omega plus and omega minus?
So yeah, I'm being a little vague about the definitions, and this is just a cartoon image. But you can think of omega minus as what is going on, like if you just restrict to this line here that is going in a stable direction.
Okay, what about the other direction? Because I thought in this other direction, you don't have the velocity.
Yeah, so in this other direction, it's uniform, but what would happen is instead, if we took the support of B1 and we composed it with a large negative power of the symplectic matrix, then it's going to be flipped the other way. Yeah, thank you for clarifying that.
Wait, so is one of these op ends like a to the minus k?
Yeah, so this B plus is here. K is going from negative
K is
to negative
negative
1.
power.
Yeah, so this is negative powers and this is the positive powers. Exactly.
Thanks. All questions? Okay. So let's thank Elena.